Hi, this is a very short mini lecture I wanted to do to finish up a couple of notes on operational amplifiers and how they work. So for this, I'm assuming you've already watched the previous lecture, which was about operational amplifiers, and here I just want to follow up with a couple of amplifier circuits that are extremely important to give you an idea of how to do things. So the first one I want to talk about is a voltage follower, which is in your lab packet as the second or third circuit that you build, and it's not entirely obvious what this thing is for, so I wanted to discuss it with everybody. So this circuit looks like this. This is our operational amplifier. And it looks something like this. And as always, the plus and minus 15 rails are assumed that the chip is powered. This is no longer part of the circuit that we're going to draw most of the time because it's not really relevant to understanding the circuit. It's just assumed that your power is on, in the same way that we assume that your power supply is on when we draw one with a battery. So in this circuit, we can remember our magic op-amp rules. The magic op-amp rules are that V out is always such so that V in is equal to that V minus is equal to V plus. And the second op-amp rule being that the current in both of these is 0, that there's no current enters the thing, and that there's as much current as we like, as we need, that comes out of this, that the thing operates like a power supply and can provide as much current as is required. Of course, these assumptions break down at some point. So if we use the first op-amp rule to look at this, so op-amp rule is this, op-amp true rule is this, is that In equals 0, I plus equals I minus equals 0. If we lose the first rule, well, it says that V out is such that V plus is equal to V minus. But V plus is just V in, and V minus is connected to V out, therefore V in equals V out. Okay, well, why would you ever use such a device? This makes no sense. Why would I have something that takes a voltage and outputs the same voltage, right? Especially if the voltage is conveying the information that we want. So, for instance, this is the audio channel that we're recording, or video, or whatever. This is a line. Why would you just want to do this? Well, the reason is, I mean, we can make a copy of it pretty easily, right, just by making a T. The reason is because we have to think about the secondary characteristics of it, what an op-amp is. Let's say I wanted to use this signal to do something. So let's say I've got a V in, and I want to put this into a speaker. A speaker has only 8 ohms, and so let's say this is 10 volts, peak to peak, let's say. Well, if this is 10 volts peak to peak, then that means we need it's going up and down by 5 volts. So the maximum, so the current this thing needs when it's at the top, when it's at the peak of this, would be 5 volts divided by 8 ohms. But that's almost an amp. That's like that's 5/8 of an amp, right? Is a lot of current. Now, if this guy back here is being powered by some lightweight component, like, say, a phonograph, the needle on a phonograph, or a cassette player, or an MP3 player, this is going to, like, half an amp is a lot of energy to turn out there. So, what we can use this guy for is we can put him in between. So we put the follower in there, like that. Now what you see, now what current is this guy driving? Well, there's no current goes into the op-amp. So this entrance point here, I is equal to 0. So if this circuit here only has to raise the voltage up just to provide just enough current for this thing to work, like nanoamps, microamps, in order to turn this thing on. This is not really 0. It's really a very small number. But a small number is good, because that means it doesn't have to provide any energy. Meanwhile, this voltage here can have as much current as you like coming out, because that's what the op-amp does, up to the maximum rating of the op-amp. So what this thing has is it has an input impedance that is very small. It's 0 in the ideal case, but of course it's not really 0. And an output impedance that, I should say, input impedance that's infinite, it's very big. It doesn't require much current. And an output impedance that's close to 0, which is to say this thing, that the Thevenin equivalent of this guy is like a power supply. That it can provide any quantity of current that you like. So that's the idea behind this. He doesn't take any current, so his input resistance is infinite, just like a voltmeter, just like an oscilloscope, which is in fact this is the first thing you see in a voltmeter and oscilloscope. And the output can provide as much current as you like. That is to say, it has an output resistance that's very low. All right. Okay, I messed up that one a little bit. Let's see if I can do the next one right. So the next one I want to talk about is a summing amplifier. Now, adding voltages is something that's actually quite difficult. If I have V1 and V2, finding something that's V3 is hard. Now, finding something that adds the currents is easy. If I have a current being injected this way and a current being injected this way, then I can just bring them together, and the current coming out of there is the sum of them. So, but the voltages aren't. So we want something that adds voltages. So to do that, I'm going to build a summing amp. And so that's going to look like this. It's going to be V1, I'll call this R1, V2, which is another input, and R2. And if we wanted, we could have V3, V4, and so on, with R3 and so on. And I'm going to take this and I'm going to put this into my op amp. And I'll tie the positive side to ground. You'll notice that when I'm doing this, I frequently flip the plus and minus to be top and bottom, depending on which way I want to draw it. There's no convention for whether plus or minus goes on top or bottom. So I can draw it upside down if I like. Now I have to have feedback, so I need a feedback resistor. And this is the whole circuit. So what does this guy do? Let's walk through him using our magic rules. Well, I know no current enters here or here because of Rule 2. And Rule 1 says that the voltage here and the voltage here will be the same, that the V out will be changed so those two are 0. Now the V plus is grounded, so the V minus, therefore, must equal 0. So, this voltage is 0, so let's say I'm going to define a current here, and I'll call it I. I'll call it IF, because it's the feedback current. Well, if V out is positive, and this is 0, then the current's running this way, and so this feedback current is going to be equal to V out over RF. But now that current doesn't enter into the minus side, so all that current continues going this way. So that current is still going here, and now this is sitting at 0, and now V1 and V2 are also, now they must be less than that 0. Okay, okay, let's bear with me. So if that's true, V minus V1 is equal to R1. Let's just call this I1 that way. Call this I1 that way. Let's start this again. I should just re-record this video, but I'm too lazy. So let's do it this way. Let's say I1 and I2 are in these directions. So V1 minus V minus is equal to I1 R1. V2 minus V minus equals I2 R2. But of course V minus is just 0, so that column goes away. And now I know that I1 plus I2 equals negative I, because I drew this one this way and these two this way, so all those must sum to 0. So I1 plus I2 plus I plus IF must sum to 0. Okay, so that means I can put these two together. So I can say V1 over R1 is I1. V2 over R2 is I2. I1 plus I2 is equal to minus I equals V1 over R1 plus V2 over R2. But also I can know that this is my feedback current, I know that's equal to this. So now I get V out over RF equals negative V1 over R1 minus V2. Oh, I'm sorry. My face is in the way. Minus V2 over R2. So what is this? Or let's write that as a minus and make that a plus. So if I make all of these resistors the same, for instance, I make them all 1K, right, then that would cancel out. And what I would have is V out equals negative V1 plus V2. So what the output voltage here is the inversion of V1 plus V2, which accomplishes our goal. Hey, we add our voltages together. If I want to have the positive sum of this, I could just run this through another inverting amp with a gain of 1. Now if I have different values for R1, R2, and RF, those become coefficients. So, for instance, if I wanted to have, say, 2 times V1 plus 3 times V2, all I would need to do is assign the RF and the R1 and the R2 values so that RF over R1 had a value of 2 and RF over R2 had a value of 3. That's not hard. I can pick, and I have actually a freedom. This is actually under constrained. What I'd have to do is pick a value of the feedback resistor that I thought was appropriate, like 1K or 10K, something like that. Something hefty enough that it's not hard to drive the currents around. So I picked something there for that, and then I could pick the other two to give me whatever I wanted. So this thing is actually an algebra solver, and it can take any number of inputs. Right? Now, one of the problems that you have in the homework is actually doing the opposite of this, and that's a difference amplifier. This thing adds voltages. It takes the negative of it, but it adds voltages. The one you have in your homework finds the difference between voltages, and you should be able to prove that using the same logic op-amp rules. Okay, I'll end this video here. Sorry I'm making mistakes, but I'm too lazy to go back and fix them, and you just have to live with it. Okay, on to the next thing.